I wish I were that eloquent with words. Okay, so let's talk about scalability for 29 minutes, right? So ask questions anytime if you want to. Just raise your hand. Don't feel like you have to wait till the end. And slides will be posted and so forth and so on. This is my contact information. Hit me up anytime. Go follow me on Twitter. I'm going to check my Twitter graph. If it doesn't go up, I'm going to really feel sad. So this is going to be a combination of a couple of different things. One is about operating complex systems at load and what really happens to them as we get them near the edges, the edges of what they're capable of doing, because it's really weird and nonlinear. And Eben Freeman just gave a mind-blowing talk about queuing theory, which is kind of the theoretical background for a lot of this stuff. And if you did not see his talk just before in the room next door, I was there. I've never seen anybody explain it so clearly and intuitively, and you will get a lot out of that. So make sure that you watch, if this is of interest to you, make sure that you watch that video later. That was just phenomenal. So let's talk about what happens to systems as we load them and why and how we can reason about that. So I take this back to a little bit of a different domain. If you're familiar with the Richard Cook and so forth and so on, and how complex systems fail and all that kind of stuff, if you've gone to any of the Velocity conference and seen John Allspaw talk about these kinds of things, there's this analogy of how systems fail in sort of not load ways, but in terms of safety, what makes systems safe to operate. And he describes this operating domain and different boundaries around it. And a lot of the focus there has been, on the left-hand side of this, on the boundary of when a system and its operators kind of jointly become unsafe. The system starts breaking down in terms of people are making decisions, the system kind of sabotages them, things kind of get really gnarly. And he draws this little line there and says, when you're approaching the marginal boundary of safety, then you start to get into this region where you're operating kind of unsafely, right? He didn't talk much about the unacceptable workload boundary. In fact, I don't know if they talked about that at all. But it's just as real. And importantly, it is also it is not a sharp boundary. There are squishy boundaries on all sides of how we operate our systems, right? It's a gradient, so I've drawn these little blue triangles. And if you read How Complex Systems Fail, these same researchers are describing lots and lots of different precepts that are very true, both about how we can operate systems safely as well as what happens to systems under load. And number 5 here is just one example, and that systems are always operating in some kind of a degraded mode. And I've spent a lot of my career doing things like debugging weird performance problems where systems will lock up for a split second or a couple of seconds and then start working again. And although this is not something that we want to happen, like you never like your MySQL server to lock up and do nothing and become unresponsible for 5 or 10 seconds or a minute or something, if you were looking at it at the microsecond, even the millisecond level, you would see this happening constantly because this is just how systems work. And we don't really realize this until we start looking at the mechanics of it at a really fine grain. So this is not a crisp domain. As we get close to it, things start getting sticky and less responsive. And if just the concept of responsiveness about systems in general is a really interesting thing to noodle about. It's a little bit different than, for example, latency or performance or things like that we're kind of used to thinking about. And I wanted to dig into that today, as well as explain kind of the mechanics underlying some of that stuff. So this region that you get into when you put your systems under higher and higher load is really hard to reason about. It is so nonlinear, and as humans, we're just not really equipped for that. We're not equipped to think about things like, if I go from 50% utilization to 60% utilization, latency is going to explode. We're not really equipped to think about, like in the simple case, if you go from, let's say, 50% utilization to 75%, you have cut in half your free overhead. What you've done is you've cut your 50% of operating margin in half, and you're not really equipped as a human to think about that sort of quadrupling the latency of your systems. But that is what happens. And that's the simple case. So that it gets much gnarlier than that. So I'm not going to really go into a lot of math today or anything, but just try and build some intuition about how to think about in this region. And then you can fall back on the math to help you guide, figure out numerically what does this mean, because your intuition is almost always going to be wrong. My intuition is never right about this stuff. So the first thing is that capacity is actually not a hard fixed quantity. Systems can and do operate beyond their capacity limits, which is really weird. But it depends on how you define capacity. And there's a crisp definition of capacity that we'll talk about a little bit later, and I'll show you why this is true. So we first have to kind of build some vocabulary and some definitions of what we're talking about. And similarly for scalability. And scalability and capacity are inextricably linked. So we start with queuing theory, and this is what Eben was just talking about so eloquently. I'm not going to go into the math. It does get a little bit dense if you try and you follow through the research and how this stuff was all developed, but we don't have to know that to appreciate just kind of generally how it works. So this basically analyzes what happens when systems get busy. And busyness here is typically spoken about in terms of utilization. So like what % of the time is something actively doing a job over an interval of time. So if you have, for example, a minute, what fraction of that minute is the system doing something? If it's 30 seconds that it's spending doing work, then it's 50% utilized. This turns out to be really difficult to apply in most cases in the real world because it's hard oftentimes to get some of the parameters, tease some of the measurements out that we need to about the systems in order to understand how to model and reason about systems in classical queuing theory. Among other things, you have to know what your service time is, and that turns out to be fiendishly difficult to measure in most real systems because service time is only one component of overall latency, and it's really hard to figure out what component of latency is waiting and what componency is the job being done, which is service time. So although sometimes you can get the data that you need to model this and predict it, it often turns out to be just super, super hard. And service time is the dashed line here. The hockey stick curve is what happens to overall latency as the system gets busy. And then this hockey stick curve just goes really, really sharply upward and goes to infinity. And that turns out to be like really just, depending on, for example, the aspect ratio of this chart, you would be utterly shocked at how quickly that happens, or you would feel like it's happening more slowly than it ought to, or whatever. So these charts almost never really give us good intuition. For example, if you look at the aspect ratio of this chart, you'll see that it's really, really flattened out, which is typical. But what your systems actually do is go up really sharply immediately. It feels like, oh, my system's performance is going to kind of get a little bit worse and a little bit worse, but it's getting dramatically worse right off the bat. So that's part of why it turns out to be difficult to predict just a gut feel. So let's go from that, which is, I think, usually very difficult to apply. In my experience anyway, it's been very difficult to apply this stuff in the real world, in practice, because of all of these factors that I mentioned. So let's talk about, in a little bit different domain, where we can kind of look at a system as a black box without knowing, for example, what is the service time that it takes to do the system's work. And we can start to look kind of from the outside in. And it turns out to be surprisingly possible to figure out what's really going on inside there where you can't measure, which is cool and wonderful. So let's talk about a system that can break its work into parallel and do speed up by doing the work in parallel. So let's think of an ideal system. There's actually kind of two dimensions that we can think of this along. One is a system whose work can be parallelized, so the job actually gets shorter. And then there's another, which is a system where the jobs don't get shorter through parallelization, but you add more capacity so that you can do more jobs. And that's what's universal about the Universal Scalability Law. And we'll reason our way there a little bit at a time. I'm not going to do all the math and everything. But just intuitively, if you have a system and you double its size, you'd like it to be able to do twice as much work. This is true linear scalability. And most systems, most vendors and products that say linearly scalable and draw some chart that looks like this are not actually linearly scalable. If you do the math, it's not a straight line, and it does not point at the origin of the chart on the bottom left. So this is very much the ideal that's rarely achieved. There's very few systems that I know of that have actually achieved this. And as a fun thought exercise, I like to go, past the vendors' booths and see who has a chart that looks like this, get the numbers, and then go see if it was really linearly scalable, and it never is. So there's an equation that describes this. We don't have to talk about how we get this, but basically the throughput is lambda on top, and n is the number of the unit of concurrency, the amount of work that the system is doing, and it's over 1, just for reasons that'll become obvious on future slides. But it's just a linear function. It's just these things are multiplied together, and that gives us our straight line. So if we think about a cluster that can parallelize, do massively parallel processing, and some like traditional scatter-gather processing, and the speed up that we would get from that, let's imagine what happens if some portion of that is not parallelizable, and there almost always is. There's like a setup. In, for example, a distributed database, there's usually like some kind of the query comes in, it has to be planned, that's serialized, that part isn't parallel. Then the little chunks get farmed out, and then they bring back their partial results, and those get aggregated. That's, again, serialized. So what happens is that our execution time gets shorter, but if we parallelize like 3 times, it doesn't get 3 times shorter. It only gets kind of approaching that in the best case. And there's an equation that describes how this works. So we just add a term onto the bottom. Now you see why I left a 1 on the bottom. This is Amdahl's law. One form of writing Amdahl's law, which describes speed up. And the degenerate case of this is, imagine that instead of 3 portions on the right-hand side where we've triple parallelized, imagine if we infinitely parallelized. We would still have, in the sort of asymptotic case, we would still have those 2 little blue bars on top that can't be shortened by parallelizing things. And that's what Amdahl's law expresses. That's the sigma. And Amdahl's law kind of rolls off and gradually approaches an asymptote. And the way to think about that is that if sigma is like 5%, then we're never going to be able to reduce the execution time below 5% of the original serialized execution time. And conversely, we're never going to get more than 1 over 5% of speed up. So if we got 5% serialization, then at best we're going to get an effective speed up of 20x, right? So there's this ceiling that we start to approach, and we start to see that line rolling off there. So that's cool. That just places a fixed upper bound on our system's throughput and the amount of work that it can get done in parallel. But it gets a little bit worse, actually. If these workers have to coordinate amongst themselves, then you're actually introducing extra work into the system. And this is where things get really fun, because that service time, you remember that hockey stick curve that had the dashed line of service time going all the way across? Turns out that in a lot of systems, service time is not a fixed quantity. It actually can get bloated as the system starts to do more and more work, and service time actually then increases. And so imagine that our parallel workers have to do some kind of coordination. I call it crosstalk. It's kind of indicative of how this sort of works. Like one of them makes a call out to the other. While it's doing that, the other one stops what it's doing and starts doing some extra work. And then the first one is idle. And then the third one on the bottom also makes a call up into the middle one. So what we're really doing is all 3 of them have to do their original work. Now their time gets lengthened because they're spending some time waiting. And now they are asking each other to do a little bit of extra work. So those service times actually get inflated. And then as a result, our overall execution time on the top actually gets bumped to a little bit later. Okay? So how bad can that get? Well, if we have either n nodes in the cluster, or we have n units of parallelization, or n things trying to do stuff at once, if there is any crosstalk between those, that's actually a function, and in a worst case, it's a function of n times n minus 1, which is order n squared. So this is a quadratic cost that increases as you increase how much you're trying to do in your system. And so if we add that quadratic cost into the bottom of the equation again, we get the full-blown Universal Scalability Law, which is a function of throughput versus concurrency. As concurrency increases, or as parallelization increases, we get some increasing amount of throughput, and then if there is non-zero crosstalk, eventually we get a roll-off. And as you take the system past that point, we actually get less done. system starts thrashing and fighting with itself and asking itself to do even more and more work. And you see this pop up all over the place in real systems, like one that I'm aware of inside of MySQL, an internal implementation of mutexes. I think it was actually standard pthread mutex. A bunch of things would try and get a mutex, and it was busy, and they would go to sleep. And then the one who was using the mutex would let it loose, and it would wake up every single one of the waiters, and they would basically all do a whole bunch of work. The operating system would schedule them because they were runnable, et cetera, and then all but one of them would go back to sleep again. So lots and lots of additional work there just to wake up and go back to sleep. And that kind of thrashing would just completely kill performance. And this is not a problem anymore. That scalability problem has been fixed. But these were back in the days when we were mostly running MySQL on a few cores, and hardware was increasingly becoming higher and higher core count, and people would upgrade from 2 to 4 or 8 core servers, and they would get a lot slower. And that was often really surprising. And so what you would do is you would pin something to just a couple of CPU cores and get most of your performance back, or even get more performance because you had a faster CPU cores. So this explains why in benchmark after benchmark after benchmark, you will see usually something that looks very much like this curve that's rolling off, because they will benchmark by number of threads. Benchmark by 1 thread, 2, 4, 8, and they'll go all the way up to 128 or 256 threads, and then you'll see the system start to dramatically decrease the amount of throughput that you get. And it usually has a log-scaled axis because it's 1, 2, 4, 8, 16, et cetera. But if you were to linearly scale that x-axis, you would see something that looks very much like this. And this just explains why that happens. So that crosstalk penalty, the blue shaded area here, is the decrease from linear scalability, and it really grows fast. It grows quadratically in the worst case. And this is that nonlinear region. Now, where the arrow is pointing is kind of the system's capacity. And when I said we can run systems past their maximum capacity, that's what that means. It means that we can actually push things to the point where we start getting retrograde scalability, and it still operates. And maybe you can get to a point where it goes into the death spiral, everything becomes non-responsive, and you have to reboot the machine. But a lot of times what happens is it keeps working. It just works really, really crappy. Like latency is highly variable. Users are having a terrible experience. Things are basically unresponsive. And importantly, as you start to approach the crest of that curve, this is that failure boundary, that's that gradient. As you start to approach that, it gets really twitchy. Like you get a little bit more load and you start to see things locking up. And you get even a little bit more, and I mean, it doesn't behave smoothly. This curve has a smooth roll-off, but real systems don't run smoothly near the boundary. They run really, really jerky. They're constantly stalling and freezing and then starting again, and stalling and freezing and starting again. So I gave this talk a little while, or a version of this talk a little while ago, and heard some really interesting questions. Isn't crosstalk a design flaw? And the answer is yeah. We'd love to eliminate crosstalk, and in fact, we'd love to eliminate serialization from our designs. But in practice, it turns out that lots and lots of real things actually require crosstalk. In Eben's talk, he was alluding to there's approximations to certain algorithms that can be a lot faster than doing the full correct implementation of something that might be really burdensome. And those there's lots and lots of optimizations that you can do in those kinds of things. But generally, there are some kinds of things like consensus algorithms, like NUMA in the physical hardware. For example, if somebody is using a cache line and dirties it, and someone else is waiting for it on another core, and so these kinds of things really happen, and you can't always eliminate all of it. And then the other question is, somebody asked me recently, actually a couple of people asked, was it seemed weird to them that crosstalk would be a constant. It seemed to them like crosstalk should be a function of load, that it should get worse as load increases. But that's actually what the equation encodes. So just to clarify that, that this crosstalk penalty is not constant at all. It's a quadratic function. And then the next question is, well, how do we measure? Like, how do we measure serialization and crosstalk? And the genius of this is we don't have to. And that's why the USL is so cool. Because it's unlike there's this whole set of equations that describe queuing theory, which are very, very gnarly. This one's actually really simple. And super easy to fit with standard curve fitting techniques, regression, things like that. And so we don't actually have to. We can estimate by just measuring. And here's the other brilliant part of this, or fortunate part, I guess, is that the measurements that we need to get are really easy to get. So a lot of times we can get these metrics right out of our monitoring systems. We may be gathering these already. For example, in MySQL, concurrency is threads running, and throughput is the questions. And those are both standard status variables that have been in MySQL since forever. So what you do is you measure those things that are on the axes, like concurrency and throughput, and you plot them in a scatter chart. You don't have to plot them, but just visually illustrating how this works. And you plot them, and then you can just do the curve fitting, and you get your estimates of the parameters. And this isn't correct. It's not like a measurement. It's an estimate. Regression can get fooled by things. That's why you plot it, so that you can see if your data is messy. This data is actually really clean. A lot of real systems look much, much messier than this. But you get an estimate of the amount of impacts of each of these parameters, the sigma and kappa. By the way, if you want this data, I tweeted about it earlier. I just put a spreadsheet which has not only the data, but a model that you can use to solve this in a Dropbox link in my Twitter account. So, if you're like me and you want to go grab the data and mess with it, it's there. There's also a calculator here. I don't expect everybody to be able to write this down really quickly, but you can just mess around with the parameters. In fact, I can probably do this and show you how sensitive this is. So sigma I've done as S here because Desmos doesn't really like Greek letters, but both of these are 3%, and if I just knock this down a little bit, we'll see that it's really, really twitchy. It's very, very sensitive. Kappa it's super, super sensitive to kappa. Whereas sigma, that serialization thing, basically has a more gradual effect. So if you want to mess with that, it's there. So scalability is actually a formal mathematical function. For so long I was like, what is scalability? Well, it's kind of this thing where if you, and it all sort of turned into word soup. And this clarified things a lot for me. I didn't invent this, by the way. It comes from a man named Neil Gunther. And it is formally derived from queuing theory. So this isn't something that somebody just sort of pulled out of the air and said, it looks right. It is right. It's not always perfect. Systems don't always behave exactly according to this, but it is a model that comes from first principles and was derived from logic and lots of formalisms, and has, it is proven equivalent to various kinds of things in the physical world. So I was talking about what happens when we load systems heavily. And so now we can talk clearly about load as well. So load is really concurrency. I already talked about how you can measure this. And now I want to talk about some great uses of the Universal Scalability Law, just to make this really practical. So one is that we can forecast beyond the observable limits on our systems. We love to load test. Who's done load testing? All right, so like a third or maybe even half of us have done load testing. Was it easy to set up realistic load tests? Heads are shaking all over the place. No, you can never set it up. You always got some kind of clean room thing. You have no confidence in it. And yet you can't observe your systems, operating near the boundaries of where you think you're going to get on the Black Friday, Cyber Monday spikes and things like that. Well, this is a way that you can try and predict. So I've got a real set of systems here. This was a benchmark, so it's nice, clean data. And you basically fit the model to this, and then you extrapolate out, and you see where it goes. And if we punch in the rest of the values, we see that it was actually pretty close. This is pretty common to be able to do this. And you can, that says pot and eyeball. It's supposed to say plot. You can you can often find systems that are really messy, but a lot of systems are actually not too hard to model this way as well. Coda Hale has written about this, great blog post. Go read that as well. And of course, there's the original Neil Gunther, who's written exhaustively about it. So you estimate those parameters, and you can quote-unquote load test beyond the real load that you're going to be able to experience. Now, the USL is actually a worst-case model. For example, that quadratic function, it doesn't have to be that bad. So you should expect your systems to scale better than this. But for capacity planning, you should actually count on them not scaling this well, is my personal experience. So, it's kind of a love-hate relationship with the USL. It's sort of like, the lower bound of what we should expect, but the upper bound of what we can hope for. And then when we analyze a system, get these measurements out of it, we can answer questions about, well, what is actually constraining scalability in this system? So there was these series of blog posts, or I guess it was just one blog post a little while ago from PayPal, where they talked about switching from Java to Node.js, and they had some benchmarks, and I was like, perfect, this data looks like very cleanly modelable. And sure enough, it is, and it turns out that Node.js was totally serialized, and Java was totally crosstalk bound. And that kind of thing is often really easy to see. Like, the reason that we're we're not getting the payback that we expect as we scale our systems is because we're wasting too much time in one or the other of these areas. So it can help you to understand where to look for improvements. We can set expectations. Without any kind of a model, you could make any claim you wanted about your systems, and nobody would be able to argue with you. But with a model that's actually based on physical reality, you can have some expectations, and it really hones the conversation. A lot of people have, there's this weird thing where venture capitalists will send me emails about companies that they're considering investing in that are particularly like parallel databases and things like that. And they'll ask me what I think of them, and I'll say, well, just give me the benchmark. And then I'll just do a quick little amount of math and send it back, and I'll be like, do you see how this system gets up to a high node count? It's basically not doing any useful work anymore. There's a real problem with the implementation here. It sounds impressive that we scaled our database to 18 nodes and got 4,000 queries per second. But I'm like, okay, so you've got 18 nodes. Each of them now has a trivial amount of data because you've distributed that data all around, and yet each node is doing 220 queries per second per node on a tiny amount of data. That's ridiculous. Like, there's a huge bottleneck in this system, and somebody needs to find it and fix it. So I get lots and lots of interesting things like that. So you can just do this really simple math and figure out whether things are scalable or not. And the trick for this is a picture from CitusDB and an animation from their homepage. CitusDB is not one of these systems that's miserably scalable, by the way. But they just have this really nice animation. And I show it here because the animation looks good, but everybody's architecture slide looks good, and yet the reality of the actual performance might be terrible. So just something to be aware of. And then finally, teams work like systems too. I mean, let's not dehumanize ourselves, but let's acknowledge that the more that we require, this is why Amazon has the 2-pizza rule, for example. Large teams have to do a lot more overhead of communication. Many small teams can get a lot more done than one large team. And this is just this old trade-off: to go far, to go fast, go alone; to go far, go together. The more that you have people coordinating and synchronizing and arriving at shared understandings and so forth, the more communication overhead you have. And Adrian Collier wrote specifically about the Universal Scalability Law in the context of teams. And ultimately, this actually goes back to Brooks's law. This good old Brooks's law describes this really clearly. There's a whole bunch of other stuff, but I'm out of time, so I'll just point you to some resources that I wrote, and you can grab these from VividCortex.com. And here's the original, perfdynamics.com is the source of everything, the original source. Thank you very much.